We will introduce two more rules in this section. The first one is if S is a finite sample space and say A is an event in the sample space, we're going to use this notation to denote the complement of A. That means the elements that's not in A, so the complement of A. So the probability of the complement of A is 1 minus probability of A. Basically, this is saying the probability of event A that is not occurring is equal to 1 minus the probability A is occurring. So this is the complement rule. The second one is the so-called inclusion-exclusion rule, which can be visualized quite easily by a Venn diagram. It is not a rigorous proof, but we just want to visualize it and skipping the proof. This is the number of elements in A union B. So let's take a look at, say, this is the sample space. You have a set A and you have a set B. A union B will be this shaded area. That's the union of A and B. And it is equal to number of elements in A plus the number of elements in B. Well, when you look at that, number of elements in A plus the number of elements in B, you can see that this common area has been added twice because it's in A and it's also in B. So therefore, we have to get the correct count, we have to subtract that area once, so which is the number of elements in the intersection of A and B. Now, this is the inclusion-exclusion rule for union of two sets. By the way, because this is also, when you count the elements in A and union B, you add, but you need to subtract the portion that's being added twice. This is also called a more, generally speaking, this is another addition rule. That's why we put this in this section, the addition rule, this section. So this is a more general version compared to previous one. The previous one, when A and B, they are disjoint, we just simply add them. So when they're not disjoint, in this case, we have to subtract the number of elements in the intersection. So this is more general situation. So this is more general addition rule. When we have three sets, this is what it is. Number of elements in A union B union C is equal to number of elements in A plus number of elements in B plus number of elements in C minus the intersection of each pair, and then plus the intersection of all these sets, all these three sets, because when you subtract those, the intersection of these three sets has been subtracted more than it's supposed to be, so we have to add it back. Well, again, you can visualize this actually by drawing in a Venn diagram to visualize it. A, B, C. So A, B, C. You can see that number of elements in A plus the number of elements in B plus the number of elements in C. Okay, when you do that, this has been added twice. This has been added twice. This has been added twice. Okay, and also this common area has been added, three times. So therefore, you have to subtract each one of those and then add this back. So that's it. That's not a rigorous proof. Again, we just want to visualize what's happening. Let's take a look at the application of these rules. The first problem is how many integers from 1 through 1,000 are multiples of 3 or 5. So we have two sets of numbers. So we need to find So this is what we need to find, the number of the union of two sets. The first set is the numbers, the integers, divisible by 3. Or, that's where the union comes in, the numbers divisible by 5, right? By 5, okay? So the or interprets as the union. Well, certainly you can count the numbers from 1 through 1,000 that are divisible by 3 using one of the earlier techniques. Say for instance 1, 2, 3, 4, 5, 6, and so on and so forth, and 999, 1,000. So you can count, this is 1 times 3. This is 2 times 3. This is 333 times 3. And once you write that, you can count in a list 1 to 333. So that means the number, the integers divisible by 3, there are 333 such integers. Now here's a shortcut. In fact, if you want to count the number of integers from 1 to a certain number and divisible by, say, 3 in this case, you can just take a floor function. So floor function, we use this as a floor function, 1,000 over 3, okay? So in this case, which is 1,000 divided by 3 is 333.33 and so on and so forth. So 3 will be repeating. And the floor function means the greatest integer that is less than or equal to 333.33. So basically you ignore the decimal. You just take the integral part. That's what it is. So therefore this is going to be 333. That's the number of integers divisible by 3. Okay, that's that number. Similarly, the number of integer divisible by 5 would be, so you take the floor function of 1,000 divided by 5, because it's just even number, it's 200 even, so therefore it's going to be 200. Now we have to count a number of these sets union, these sets, right? So we have to subtract the intersection. So the intersection of the numbers divisible by 3 and at the same time divisible by 5, those are the numbers that are divisible by 15. So the numbers divisible by 3 and at the same time divisible by 5, that's the numbers divisible by 15. So the number of integers divisible by 15, using this shortcut, 1,000 divided by 15. So if you do that, this is going to be 66. Just take the integral part. Now, time for us to apply this rule, inclusion-exclusion rule, which is also called a general addition rule for two sets. So it is equal to the number of the integers divisible by 3 plus, so we are applying this rule, plus the number of, so this is our set A, this is the set B. So now plus the number of the integers divisible by 5, okay, then minus the number of the integers, the number of those numbers divisible by 15, right? 15. And we have those numbers ready here. 333 plus 200 and then minus 66. So this is 533 minus 66, 533, which is 467. 467. So that's how many integers from 1 through 100, 1,000, multiples of 3 or 5. We okay. By the way, you cannot just add these two, simply add these two, because there are numbers that are at the same time multiple of 3 and multiple of 5. So that will be, if you add them, those will be added twice. That's why we have to subtract once. Now let's talk about probability. Randomly select a number from 1 through 1,000. What is the probability that it is neither a multiple of 3 nor a multiple of 5? Okay, nor a multiple of 5. So neither nor, right? Neither nor. So that means we already found the numbers of integers that are divisible by 3 or divisible by 5. And this neither a multiple of 3 or nor a multiple of 5, which is the complement of this guy. So therefore, it is going to be 1 minus the probability of the above. So 1 minus the probability of divisible by 3 or 5, right? So therefore, it's going to be 1 minus. And the chance of a number, randomly selected number that's divisible by 3 or 5, it's 467 over how many numbers? From 1 to 1,000, that's 1,000 number. So therefore, this is equal to 533 over 1,000. So that's the probability.